This is a circuit designed for amplitude modulation. First, we need to place B source into the template. We can rename the source as a information signal. Then we can repeat the process and rename it into carrier signal. Next, we need to determine the amplitude and the frequency of the signal. For information signal, the amplitude will be 1.1 and the frequency will be 100 Hz. Since this is in radian per second, we will add times 2 times pi to represent the omega. For the carrier signal, the amplitude will be 1.2. Since a carrier signal amplitude need to be higher than the information signal, and the frequency will be 1000 Hz. Next, we need to multiply both signals by using the product template. The output of the signal need to be added with the carrier signal itself. Thus, we have the complete modulated signal by using only an add block and multiply block. We can monitor the output by logging the signals. Besides that, we need to adjust the step size. Since this circuit simulates in a high frequency, which is 1000 Hz, we can modify the maximum step size of the simulation. After running the simulation, we can display the waveform by using data inspector. We can adjust the scale of the period to find the best image that we need to see. From the graph, we can say that the signal is successfully modulated. Now we need to design a demodulator circuit. First, we need to multiply the output signal with the carrier signal itself as a local source from the receiver, which has the same frequency with the carrier signal. We can also label our wire since our circuits will become more complex. This is the result of multiplying the modulated signal with the carrier signal itself. Finally, we need to smooth the output waveform since it does not represent the actual information signal. We can use a low pass filter by placing a transfer function into the template. The transfer function for low pass filter is equals to A naught over S plus omega naught. Omega naught is the cut-off frequency and it is equals to 1 over RC. So we can put the numerator equals to our information signal frequency and the denominator as well. So the output of the low pass filter will filter the high frequency from the low frequency signal. But as we can see, the output signal is jagged and not as smooth as the information signal. So we need to further smooth the signal by placing another low pass filter. For this case, I will use up to 3 low pass filters. Then the final output should be equals to the information signal. By using low pass filter, we can see that the output is shifted in terms of its phase by 45 degrees per RC filter. The signal need to be go through an amplitude modulation before it is ready to be the actual information signal. We can also monitor the actual sideband that we have with our modulating signal. We can use a rate transition to limit our sample data, since we need to use the spectrum analyzer. The output port sample time can be set to be equal to our uh, high frequency. For this case is the carrier signal. Finally, the spectrum analyzer require high number of samples. Then we need to increase our stop time. As we can see, the spectrum analyzer shows that the frequency for carrier is equals to 1 kilohertz and the sideband plus 100 to the right or minus 100. That's all for today. Thank you very much. Arigato. Sayonara.